All right, so hello, welcome to class. We're starting on our next topic, electricity, and then circuits we're also going to get into. Um, so just a reminder, if you haven't, please get your test turned in. So test and any late work, especially that test and the Thanksgiving quiz, get those in so I can give you grades for those. Um, if you know people's phone numbers, just contact them and see if they submitted the take-home test. The faster, or not the take-home test, the actual waves test, the faster we get all of those in, the faster I can give you your specific results. I'm going to grade those and you'll get a grade in the grade book, but the faster you get back to me with the vast majority of people having the test turned in, I can actually give you your individual results. All right, so get that done, get that in. Um, I don't know how many topics we're going to end up doing for the rest of the year. We're kind of skipping one for now, light and optics, in favor of electricity and circuits. I think it's going to be a little bit easier to teach this one online. But yeah, we'll see. It'll probably be this and one other topic. So it's between magnetism and light and optics. So we'll kind of see. We'll decide at some point. All right. So moving on. So we're dealing with electricity. At the most basic, what is electricity? Anyone know? At its most basic, what is electricity? Energy. So there is energy. There is electrical energy, and you will have also power. So that is one thing we're going to have. We still have electrical power is going to be change in energy over time. So when you look at a light bulb, it's rated in watts, so rated in powers that uses electricity. Yeah, this is notes. You have like a computer power supply. The computer power supply might be 750 watts, 1,000 watts, 600 watts, something like that. So yeah, you do have electrical power, electrical energy. But what is electricity? Like when you flip on a switch, what are you actually sending? What's actually moving through those wires? Anyone? What's the actual stuff moving through the wires? So yeah, but what is electricity though? That's the question. So yeah, it is electricity moving through the wires. But what is physically moving through the wires? What like actual thing? It's not magic. I don't flip a switch and then magic turns all the lights on. I mean, it's going to be some sort of particle, some sort of subatomic particle. So electrons, that's what normally we're going to be looking at. It doesn't even have to be electrons though. It's electrons are specifically a charged particle, but electricity is going to be a flow of charged particles. So when you flip on your switch, yeah, it's letting electrons move through the wires. Those electrons carry energy. That electron delivers a certain amount of energy per time, and that gives us power. So electrons are a charged particle, so we can look at electrons. And if you look at your formula chart at the very, very bottom, we have some constants there for a lot of different values. So if you're looking at your formula chart, we have a lot of these different constants. Obviously, electrons are going to be the big things we look at. Whenever I look at an atom, actually, let's just go here. So electron, so we do have mass of an electron. They're really, really small. So this is going to be 9.11 times 10 to the negative 31st kilograms. And this also has a charge. We're going to call Q charge of positive or negative for an electron. Are electrons positively charged or negative? So electrons are negatively charged. Negative 1.6 times 10 to the negative 19 coulombs. All right. Now, coulomb is a new unit. Now, a lot of times whenever we look at something, we can measure something directly. If I use a ruler, I can directly measure length in meters. If I have a timer, I can directly measure time in seconds. If I have a scale, I can measure mass in kilograms. These are all fundamental units. I can't break them down into anything smaller. This is the same thing with a coulomb. A coulomb is a fundamental unit. It can't be broken down into smaller quantities. It's not like kinetic energy is kilograms, meters squared per second squared, or speed is meters per second. A coulomb is just a coulomb. In fact, we kind of define a coulomb as the amount of charge carried by 1.6 times 10 to the 19 electrons. So we have this tiny amount of coulombs, so it's more the amount of electrons we need to have that many coulombs. So this is a fundamental quantity that we're not actually going to measure. So electrons carry a charge. What's the other subatomic particle that carries a charge, though? So we also have protons. All right, so we have protons, and the mass of a proton. Protons are a lot more massive than electrons, still tiny, but a lot more massive. So 1.67 times 10 to the negative 27th kilograms, over 1,000 times the mass of an electron. And then a proton, this is charge of an electron, charge of a proton, has an identical charge to the electron. But what's different about the charge of a proton? So protons are positive. So you should have learned all this in chemistry, right? You have electrons in an atom, you have protons in an atom. Then we have neutrons. Neutrons don't have a charge, so we're not caring about those here because electricity is the flow of charged particles. And then if you look at an uncharged atom, they have the same number of electrons and protons. They have the same amount of negative and positive charge. So if I have a hydrogen atom with one proton and one electron, because the electron and protons have the same charge but opposite quantity, that means I have zero net charge. So these are the two fundamental particles that can carry charge, and I can move these. Which one of these is easier to move? Which one of those is stuck in place, and which one of those can I move pretty easily? So we can move electrons. So electrons, you may have done this in chemistry, like electron orbitals. I'm not gonna electron orbitals. We've known that's like a bad notion for over 100 years. It's what's in called. It's what's in the electron cloud. So these things actually move around in these like random shapes that we can measure, and they make some really cool shapes. So if you've actually seen the electron structures, they're way more interesting than just like those little circles that you draw. So not orbital, but yeah, the electrons are outside of the nucleus. That means they're easy to move. But our protons are stuck in the nucleus. Now, we've only been over a few forces in here. So we've talked about force of gravity. Today we're going to talk about the electric force, and then that can be combined with the magnetic force. So there's two other forces we haven't talked about, the strong nuclear force and the weak nuclear force. I'm just going to say that strong nuclear force that keeps the protons stuck in the nucleus is absolutely massive. This is the reason atomic bombs exist. This is the reason that atomic bombs can like wipe out entire like cities. That strong nuclear force is so massively strong. So these protons are really, really, really stuck in the nucleus. So if we want to make these moves, so how to move a proton? So how to remove proton from the nucleus. All right, if we really want to remove a proton from the nucleus, one, use an atomic bomb. And I'm going to use nuclear as a better way. So use a nuclear bomb, rip those apart. That's one way. Another way, giant particle accelerator. That's one way of doing this. Or we could have a large star or a black hole. This is what it would take to actually pull one of those protons out of the nucleus. So it's not impossible to move a proton. We can do these things. We do have nuclear bombs. We have giant particle accelerators. But we're not really going to be dealing with moving protons. The electrons are going to be the things that are easy to move. So when we're talking about electricity, pretty much always in here, we're going to be talking about the flow of electrons. Now, wouldn't change the proton. So all those chemists that were trying to like make gold by like playing around with things that looked yellow, which I think that was you who actually told me about the person who was trying to turn urine into gold because they were like looked similar enough. So yeah, chemists were trying to do that for like thousands of years and they couldn't do it. And then physicists came along and were like, yeah, you know what? We know how to make gold. So yeah, it took a physicist to actually turn things into gold. So yeah, we can change what an actual thing is, and we do that quite frequently. That's kind of outside the scope of this class, but yeah, so physics can do that. Chemistry can borrow physics to do that, but yeah. So we're talking mostly the flow of electrons, and then kind of a little side note. We're not going to go so much into this, but the electrons themselves actually don't move very fast through a wire. When we're looking at electrons, the electrons are moving through a wire at about this speed. They're not going very fast. It's actually the energy that's transferred really fast. So just something I'm not really going to test you about, but just kind of a thing to know. The electrons don't move through the wire so fast. The energy flows through the wire really fast. All right, so electricity, we're dealing with the flow of electrons. We can have a positive charge, we can have a negative charge. Now, we'll get into electric currents and voltages and things like that at a later point. Today, what we're going to kind of focus more on is our fundamental charges. So these are our smallest possible charges we can have. I can't have a charge any less than 1.6 times 10 to the negative 19 coulombs. So electrons and protons are the smallest possible charges we could have. Then how do lights? So it's through electric fields. So the thing I was talking about, that electromagnetic force, when the electron moves, it creates a magnetic field. That magnetic field changes, which moves another electron. So it's fields moving. It's the energy that's moving at the speed of light, but it's not the electrons moving. So it's the electrons that are actually moving that is the electricity, but when the electrons move, they generate these things that are like electromagnetic fields, and so it's the energy that's being transmitted through that goes at the speed of light in the material. Yeah, so we have our fundamental units. If I were to rip apart an electron, or if I were to rip apart a proton, which again, we can actually do this, we can rip those down into their fundamental units, which are quarks, those won't have a charge anymore. So these are smallest possible charges, which is what we call our fundamental charge. So this is going to be our fundamental charge. I can't have anything smaller than this. Charge. So this is the smallest possible charge I can have. I can't have anything less than 1.6 times 10 to the negative 19 coulombs. And then the other thing we're going to be looking at today, before we actually get into electricity and circuits and things like that, is we're going to be talking about the electric force. And if we do go into magnetism, we will see that it's actually the electromagnetic force. For the longest time, physicists were just playing around with electric spheres, and then they were playing around with magnets, and they were like, hey, these things are fun, and they were completely different. Until some really smart people came along and noticed, hey, like Faraday and other physicists noticed, hey, one of these affect each other. The electric force affects the magnetic force. And then Maxwell combined them into one force, electromagnetic. So we're kind of like way back in like the late 1700s, early 1800s with this. So we're moving past Newton, but we're still hundreds of years in the past with this. So we have our electric force, and this was made by Coulomb, Coulomb's law. Coulomb's law. Again, you don't get to name things after yourself. It was named after him. I don't know if he was dead yet. It was probably at least close to dead before it was named after him. All right, so we have this electric force is going to be a constant times charge 1 times charge 2 divided by the distance from center to center of the two objects squared. What does this look really similar to? This looks really similar to an equation we've seen before. Not Doppler effect. It's one that Newton did. What was Newton known for? What force did he deal a lot with? Force of gravity. So we know the force of gravity is that gravitational constant times mass 1 times mass 2 divided by distance squared. So we see these are very similar looking. So G was our gravitational constant. That's 6.67 times 10 to the negative 11. K is going to be our electric constant. Let me make sure I get the units right. So it's 9 times 10 to the 9th. Should be newtons meter squared per coulomb squared. Newtons meter squared per coulomb squared. Let me look at this to make sure I'm not saying something stupid. Yes, newtons meter squared per coulomb squared. 9 times 10 to the 9th. Einstein did a lot with gravity. He kind of proved that this doesn't work for large masses or high speeds. So, yeah, Einstein kind of disproved a portion of Newton. So 9 times 10 to the 9. 10 to the 9, that's a billion. 9 billion. That is a pretty big number, right? Our gravitational constant here, this was only 6.67 times 10 to the negative 11. Again, this is one that I always like forget the units for because they're super weird. Meters cubed per kilogram second squared. So just looking at these two constants, which of these forces is more powerful? Yeah, 9 billion versus, what is that, like 100 billionths? We're talking about like 10 to the 20 more. Like the difference between these two would be saying like Jeff Bezos has like what, like 150 billion dollars, and some like 4-year-old kid picked up a penny off the sidewalk. Like that's like the difference between these two constants. So the gravitational force is an insanely weak force. Just think about what I need to experience a gravitational force. I'm not so massive, but I need this giant Earth in order to fill any sort of weight. So I have a really, really weak gravitational force, but our electric force is really big. Which again, what's holding our atoms together? What's holding our electrons to the nucleus? We have a negatively charged electron, positively charged proton. So it's this opposite charge, the electric force holding our electrons to our protons, right? So we have, this is what's holding our electrons together. This is what's holding all of our atoms together, at least the electrons to our atoms. All of the chemical bonding is happening between electrons and protons, right? The electron structure you've seen in chemistry. So these tiny, tiny, tiny objects are able to do substantial amounts of force compared to needing a giant Earth. And this is really important. Imagine if these two forces were similar. If these two forces were comparable to each other, and I was near the Earth, well, that would say the force of gravity would be absolutely massive. Like, think of the size of the Earth, like 6 times 10 to the 24th kilograms. So if these were closer together, the Earth would literally rip apart all of my molecules, and it would rip all of the atoms away from the nucleus. Like, this would be absolutely terrifying. It would also do other things like, collapse the Earth into a black hole. But yeah, so it's really good that these are very different. We have a really weak gravitational force. This is good because I don't get thrown into walls. I'm not getting ripped apart at the molecular level. So tiny, tiny charges can have really big forces, which is important to hold everything together. But gravity is dealing with the really small forces. All right. And then this still isn't the strongest force. This is still not close to even the strong nuclear force, which is way, way more powerful than this. Yeah, again, that's how you get stars, black holes, atomic bombs, things like that. All right, then we have Q. Again, we already defined Q. Q is our electric charge. And then we have r squared, so r radius. So this is talking about a distance. Now, when we were talking about our distance from where to where? So, like, think about all the way back when we were, like, let's say we have our Earth, and then we have our moon, obviously not to scale. Where was our distance from? So, center. Yeah, from center of mass to center of mass. We're going from center to center. So, distance between the centers of the charges. All right. So, gravity. Which way can the force of gravity act? If I put my pencil here, which way does gravity act? Towards the larger source. Well, but according to Newton's third law, the Earth also got pulled up, just not enough to actually notice. So gravity is an attractive force. Gravity is always pulling the two masses together. So gravity is always attractive. But this electric force, does it always have to attract? No. So our electric force can be attractive or repulsive. So in order for this to be attractive, what type of charges attract? Are you looking for same charge, like charges, or opposite charges? I think y'all may have done this in chemistry, hopefully. So attracting, we're going to see opposite charges attract. Or am I just going too fast? What's chemistry? The thing that y'all took last year? Some of you aren't you taking that this year? So opposite charges attract. So a positive, negative will attract, or a negative, positive will attract. Science, my best definition of science is the way of analyzing the world by testing through either experimentation or direct observation in order to best create a model that most approximates reality as evidenced by its predictive power. All right, so opposite charges attract. So what type of charges are going to repel? Like charges repel. I think y'all did this in chemistry, I'm pretty sure. Um, Water and oil. That's a little bit different. That's like hydrophobic versus hydrophilic and dealing with like polar and non-polar quantities. So like charges repel. So if I have positive, positive, these are going to repel each other. Or if I have negative, negative, these are going to repel each other. Now, when I look at this, I'm dealing with my electric force. If I do a positive times a negative, or a negative times a positive, uh, it is how batteries work. Yeah, so you are just pushing charges through. There's a little bit more going on there inside a battery. There's a lot of like chemical reactions, freeing up an electron and then generating a potential that pushes it. Yeah, battery acid. Well, you need the battery acid, which is the what the heck is that called? I forget the exact word for it. But then you need like the anode and the cathode and all that. Your favorite drink. All right. So if I have opposite charges, I'm going to do a positive times a negative. So what's my electric force going to be? A positive times a negative, right? Because we have positive times a negative, we're going to get a negative. So my electric force will be negative if we have an attractive force. But here, positive times positive or negative times negative, positive times positive or negative times negative, our electric force is going to equal to, not iron, yeah, electric force. Positive times positive is a positive, negative times negative is a positive. So that's how we're going to read our electric force from Coulomb's law. If we multiply our values together and we get a negative, it means it's an attractive force. If we multiply our forces together and we get a positive, it means it's a repulsive force. The charges repel. So this is going to be something that a lot of people are going to struggle with. This positive and negative are not saying right or left. That positive or negative are saying, does this attract or does this repel? And then we're going to have to figure out directions after the fact. All right, any questions on what we've gone through in here? So we're not getting to circuits yet. We'll get to circuits probably 2 classes from now. I have a lot of circuits at home. That's the other reason I chose this, is I have a lot of things to build circuits at my house. Questions? I'll give you a little bit to catch up. New gamer's mouse. It's too heavy. I actually use like really cheap mice even for gaming. I like really small ones, which is weird because I have big hands, but I like a really small mouse. See, I like mice to be really light. $120 grams, 160 grams. Oh, I just don't like when the mouse. I don't mind the weight of it, or like, I just don't want it to be too large. Everyone's okay on this? Literally felt like air going on. You can just make it out of lead. Fun fact: uranium makes a better radiation shielding than lead does, but the amount of uranium that you would need to use in order to make radiation shielding would put off more radiation than most things you'd be shielding it from. All right, so the only thing we've really introduced today is going to be Coulomb's law, and then we're going to be using a few times we're going to be talking about the fundamental charges. Isn't osmium really toxic? Because when I was in the Navy, me and a friend were like trying to figure out ways to turn things into gold using nuclear reactors. But then we kind of settled on, hey, platinum's more expensive than gold, so our plan was to turn either iridium or osmium into platinum using nuclear reactors. It would work. Densest known. Osmium is not going to be the densest known material. That's going to be dependent on the more things than that. Maybe the chemical bonds it makes. It might be a specific one. I'd have to look into it. There's a lot more going on with bonds and structures that things make. So maybe there's a certain like. All right, so we're going to look in our textbook. I'll give you a second to open it. So we're going to go through the problems listed there. So we're on chapter 18. Problems. Oh, and I would actually have to say, it might be one of the most densest things on Earth, but there's also like neutron stars, which are definitely way more dense. So chapter 18 problems. We'll start on 18.1. We'll just kind of go through these. These are kind of starting off dealing with the fundamental charge. So, number one. First of all, one of the things we're going to see here is when we're dealing with electric forces and charges, we're going to be dealing with really, really small numbers. Again, back to that whole thing about the electric force being so much bigger than the gravitational force, which means we need not very big charges to cause larger forces. So normally we're going to see things like nanocoulombs to microcoulombs. So there is going to be quite a bit of unit conversions you need to do here. So we see how many electrons are needed to form a charge of -2 nanocoulombs. Nano. Does anyone remember what nano is off the top of their head? Close, not 9, but it's a really small, not a big number. 10 to the -9 coulombs. So a billionth of a coulomb. So things we're going to be running into. So you should already know milli. So 1 millicoulomb would be 10 to the -3 coulombs. We've seen micro a bit, but I don't think I've ever forced you to remember this. This is going to be 10 to the -6 coulombs. And then we have nanocoulombs is 10 to the -9 coulombs. So these are ones that I want you to remember. Now, obviously, if we don't go back to school and we end up having like tests and quizzes, I can't force you to memorize these. But these are ones that you should just kind of, by the time we've used these enough, you should have used these enough that you just kind of remember them. And then we can also go a little bit lower. I forget if they have any picocoulombs on here, but there's picocoulombs, 10 to the -12th coulombs. And they're definitely not going down to femtocoulombs. So things to kind of know, just kind of be expecting, like I said, all year. Towards the end of the year, we have a lot more unit conversions, and this is why we're dealing with really small charges. All right, so -2 times 10 to the -9th coulombs. We want to know how many electrons there are. So what's the charge of an electron? It is negative 1.6 times 10 to the -19 coulombs. This is on your formula chart. And again, like I said, when we actually do this test or quizzes, it's probably just going to have to be online, so I can't stop you from looking them up. All right, so we want to know how many of these fit in here. So what mathematical operation are we going to do? I want to know how many of these fit in here. What mathematical operation? Addition, subtraction, multiplication, division. Those are our mathematical operations. Yeah, division. We're going to divide. So how many of these fit in here? That's division. So I have -2 times 10 to the -9 coulombs divided by, and let's make sure we use parentheses when we put it in our calculator, 1.6 times 10 to the -19 coulombs. So I don't know your calculator situation at home. A lot of you are probably using calculators that aren't TI-84 pluses or Inspires or things like that. So again, when you put this in, let's be really careful to do -2 times 10 to the -9th divided by, and then let's put this whole denominator in parentheses, divided by negative 1.6 times 10 to the negative 19. And you should get a nice number. Lapid EMU. Or yeah, use Desmos, or yeah, there's a lot of things you can use. So yeah, we get a real nice even number. We have what did I have? I literally had it right there. Yeah, 1.25 times 10 to the 10th electrons. So yeah, electrons, there are a lot of electrons. Again, electrons are insanely, insanely tiny. Which is still kind of crazy to me, like the whole fact that an electron and a proton are like so inconceivably small, and they're still producing larger forces than the giant Earth pulls on them with gravity. All right. So, if there's no question on that, I think that's relatively straightforward. Look at 2. 2 wants to know, we have 1.8 times 10 to the 20th electrons move through a pocket calculator during a full day's operation. How many coulombs of charge moved through it? All right, so I have 1.8 times 10 to the 20th. A lot of times, electron, you can put an E minus for electron, or a positron would be an E plus. All right. But I want to get rid of this electron term. So how many coulombs do I have per electron? All right. And then negative, let's be sure to put that charge so we can see, because it says how many coulombs of charge, and I could see how many being not positive or negative, but we do have a negative value. So negative 1.6 times 10 to the negative 19 coulombs per each little electron. So I can divide out electrons there. Charge, again, charge is a Q. Sometimes you might see it a capital Q. I like lowercase q. Capital Q can be, yeah, multiply. Capital Q can be misinterpreted as heat. What do you get? Can you hear me now? All right. So yeah, so if we look at number 4, then you see a lightning bolt moves 40 coulombs of charge. This moves 28.8 coulombs of charge. Now, a coulomb is a massive amount of charge. So what's the difference between a lightning bolt delivering 40 coulombs of charge and this calculator delivering 28.8 coulombs of charge? Over a full day's operation. So how fast does the lightning bolt deliver that 40 coulombs? Really fast. So the lightning bolt delivers that charge insanely fast, like really, really fast. So this one delivers it just constantly over a really, really, really long amount of time. So a single coulomb of charge delivered to you really, really fast, that will you'll be having a bad day pretty fast. So a coulomb is a really big amount of charge. All right, so you're going to do 3 and 4 on your own. All right. I'm going to let you do, so now we're going to look at 18.2. I'm going to let you do 5, and we'll do 6 together. All right, so 6. An amoeba has 1 times 10 to the 16 protons and a net charge of positive 0.3 picocoulombs. How many fewer electrons are there than protons? And then if we pair them up, what fraction of protons would have no electrons? All right, so when we look at this, let's say I have a situation where I have positive, 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 negative, negative, negative. How much charge do I have? Yeah, there are some kind of chemistry ones in here that I strayed away from. How much charge do I have here? Well, I have 3 positive charge and 3 negative charge. So one way of looking at things is just how much total charge I have. But what would my net charge on all of this be? By the way, we're not looking at 6 quite yet. What's my net charge, though? Zero. If I have the same positives as I have negatives, positive, negative cancels out, positive, negative cancels out, positive, negative cancels out. So I would have 0 coulombs of net charge. So there's a few ways of looking at things. I can look at how much positive charge I have, how much negative charge I have, or I could look at what's my net charge. How many more positives do I have, or how many more negatives do I have? So that's what this one is kind of getting at. So we have that amoeba. It has a net charge of 0.3 picocoulombs. So net charge of positive 0.3 picocoulombs. Pico, what was pico? 10 to the negative 12 coulombs. All right, so we have a net charge of 0.3 times 10 to the negative 12 coulombs. So I want to know how many fewer electrons are there than protons. Well, net charge is talking about the difference in the charges. So this is my difference between the protons and electrons. Now, if I have a positive, What do I have more of? More protons or more electrons? So we have a positive charge, which means more protons than electrons. And a thing to kind of watch out for, again, the only thing that we can move is electrons. So to get a positive charge, we took electrons away. We didn't add the protons in, we took electrons away. Because again, if you want to move protons, you're talking about really, really high energy things. An amoeba is not operating an atomic accelerator. All right, so we have more protons and electrons. And so we have this net charge by this amount. So we just want to figure out how many electrons, or how many, what was the question? How many fewer electrons there are than protons. So how many protons this makes up. So a proton has a charge of, let's see, so I have 0.3 times 10 to the negative 12 coulombs. Well, I want to figure out how many protons I have. Well, one proton, P plus is a proton, has positive 1.6 times 10 to the negative 19 coulombs. Again, in our calculator, let's put that in parentheses. That way I can cancel out my coulombs and see how many extra protons I have. So that net charge is helping us figure out how many more of something I have than the other. So what do we get? Yeah, 1,875,000. 1,875,000 more protons than electrons. Now, B wants to know if I paired them up, what fraction of the protons would have no electrons? So what fraction of protons would have no electrons? Well, to get a fraction means dividing. So I want to know what fraction of protons, so protons without electrons divided by the total protons. All right, protons without electrons. Well, I have 1,875,000 protons without electrons. And we have 1 times 10 to the 16 protons. $10 to 20. Yeah, 10 to 20, all of 10 through 20. This is going a little bit more than I thought I would, so I'm probably just going to start on that there, and then we'll talk a little bit more about those next class. I don't want this video to get too long. So I'm probably just going to do 1 or 2 from the 10 to 20. You'll work on those, ask questions, and I expect questions about those. So what do I get when I get 1,875,000 divided by 10 to the 16? Yeah, so a really, really small number, 1.875 times 10 to the negative 10th. So to get charges, it's really only tiny, tiny amounts different. Divided by 10 to the 16, not 10 to the negative 16. And make sure you put this in parentheses. So we have a tiny amount of these. So like, what is that number? Like 1 in 10 billion, pretty much. No, 1 in 5 billion almost. So for every 5 billion protons, I take away a single electron. All right, so sections 1 and 2 are mostly like this, just dealing with the amount of electric charge on things. Hopefully that's not too bad. So 18.3 is where we start actually getting into Coulomb's law. I think it's about to storm. Yeah, it does seem like that. I think it was raining here a second ago. I'm just going to do the first one on Coulomb's law. And we'll talk about this more next class. Again, we're a little bit ahead of the other classes, so we're not going to go so much into this. Yeah, you're not going to have to finish today. I'm going to push it back. After this, I'm going to push the due date of the homework back. So yeah, work on it, and I'll go through more of this next class, and I do expect questions. So yeah. I will push that back. We'll just do 10, and then that'll be about good. Yeah, one more. 10. So what is the repulsive force between two pith balls? So pith balls are just, I don't know exactly what pith is. It's a non-conductive material that holds charges on it, more like static charges than anything else. So what is the repulsive force between two pith balls that are 8 centimeters apart and have equal charges of negative 30 nanocoulombs? Getting tired. All right, so we're dealing with our Coulomb's law. So electric force is the electric constant times charge 1 times charge 2 divided by the distance between the center of the two object squares. Yeah, we're using our Coulomb's law formula. Our constant is that 9 times 10 to the 9th newtons meters squared per coulomb squared. We have our two charges are identical. Nano, what is nano? Yeah, nano is negative 9 coulombs, negative 9 coulombs. I would suggest you're going to see micro and nano a lot. You might as well get to the point where you just remember those. Obviously, you can look it up. Yeah, pico is negative 12, yes. And then femto, negative 15. I've never had to use anything below femto without just using scientific notation. Micro is negative 6. All right. And then how far apart are these objects? How far apart are these two objects? They're 8 centimeters apart. So yeah, exactly, 0.08 meters. 0.08 meters. We need to use our fundamental constants. So meters, kilograms, seconds. But we introduced some new ones. Coulombs. So meters, kilograms, seconds, coulombs. All right, and then don't forget to square this, r squared. One of the easier ways to mess this up. So substitute those in, do your calculations, get a number. Yeah, you can just square the top instead of multiplying the 2. In fact, that's what I did in my calculator. This is just the first one we're doing, so I wasn't going to write it that way. Otherwise, people would get confused and think they can do that for all of them. Not quite. Did you multiply it by 9 times 10 to the 9th? Yeah, don't forget to multiply your constant in there. Yeah, those are probably the 2 biggest mistakes I'm going to see. People forgetting to square the denominator and people forgetting to multiply by the constant. Close, your rounding is just a little bit off. So 0.00127 newtons. We got a positive value. What did positive electric force mean? Yeah. What did that? Uh, Positive charge meant more protons, but positive force. Same charges, yeah. Okay, so yes, we get a positive force exactly when we have the like charges. So negative, negative, or positive, positive. So do they attract or repel? Yeah. So we're going to see these repel and like charges. All right. So work on these, do as much as you can. I'm going to push back the due date. I was a little bit over optimistic how much I would get through in class, but yeah, I don't want to make this video too long, otherwise people might not watch it. And I'm also trying not to stress y'all out too much while y'all are working at home. So work through these. I'll take questions up to number 10 in tutorials, but next class we'll work through some after number 10, all right? So try to do 1 through 10, or at least the assigned numbers, so 1 through 6 and number 10, maybe do a few after that if you can. So I'll answer questions about this in tutorials. I'll work on some of them after 10 next class, the next Tuesday. And then, yeah, next Friday you have off. I mean, officially an off day where no one should be assigning videos or anything. And then again, if you have any late work, get those turned in. Your test, if you haven't gotten that turned in, get your test turned in. And your take-home quiz, please get that turned in, or labs, things like that. I'm going to stop the recording now. You can stay here and still ask me questions after I stop the recording. But other than that, everyone, have a good weekend.